Hello guys, let us continue with our discussion of a sequence of Bernoulli trials. At the end of our last lecture, we wanted to set up the stage for different distributions that could arise from a sequence of Bernoulli trials. By definition, the sequence of Bernoulli trials are independent trials, independent and identical. So if we define a random variable xi for the trial number I, because they are identical, and if this random variable is to indicate the success, yeah, at trial I, so for each I, this will be a Bernoulli random variable with the same, and they will all have the same probability P of success. Remember, these will either be ones and zeros. And the best way to characterize the distribution is through the Bernoulli PGF, probability generative function, which has 1 minus P and P. So both the probability of success and the probability of failure, they appear as coefficients. And the exponents of Z, they capture the possible values. So this one as an exponent of 1 is one possible value representing the success with an associated probability P of success. And this one here means that the exponent of Z is 0. 0 encodes the failure in the language of Bernoulli, and the associated probability with failure is 1 minus P. So you can see that the PGF tells you the whole story of each and every Bernoulli random variable associated with the trials. So the different quantities of interest include these four, and today we will start with this one. So let's say X is a random variable which is going to represent the number of successes in a fixed number n of trials. Yeah, because x1 and x2 and so on, because they represent success at each trial. So if we add all of these Bernoulli random variables, you see I'll be adding ones and zeros, and I will have as many ones as there are successes. So X automatically has to be a sum of Bernoulli random variables. That's how I started it. X must be a sum of Bernoulli random variables. Now this is not just a sum of any random variables. These are all independent, identical distributed random variables. What that means is that I know a result from our previous lecture that the PGF, because if I can work out the PGF of this new random variable, PGF of this X, then I know everything about this. So the PGF, we discovered last time that the PGF G of a sum of independent variables is the product of their individual PGFs. Here I have the same situation. X is the sum of these xi's. I know the PGF of each one of them. I just have to multiply. The PGF of each one of them is P times Z. P is the success probability, 1 minus P times 1. And I raise this to nth power. And that's it. Now I have my PGF for the number of successes. If I want, I can expand this binomial series, and if I compare it with the definition of a PGF, I would expect the probabilities associated with K. So in just one go, just by expanding this binomial series, I got my PDF. This will give me the PDF. Of course, restricted to the support, so I write hash there. So I can read that off from the PGF. So I will use this for reading the PDF, and I will use this form for any other calculation which requires calculus. So you see, I could read the probability distribution from my PGF. So I have discovered a new distribution. That is what we mean by binomial distribution. If I want to say that X is distributed according to this binomial distribution, I will write BIN for binomial, and there are only two parameters. N is the number of successes. Sorry, not the number of successes, the number of trials, a fixed number of trials. And for each trial, I must know the probability of success, P. So two parameters, the number of trials, the probability of success, and I have a new distribution. Actually, a family of distribution, because for each pair of these values, N and P, I will have a different member of that family. So I can now complete my characterization of this new distribution by specifying the support. So these are the possible values. You see, 0 would mean no success in those N trials. N would mean all successes, and you can have anything in between. And the probability of K successes will, it's just that formula. And this will only be valid when K belongs to that support. So that's why we have to write this hash. And it's customary to write that same symbols BIN for the PDF as well. Not for the PDF, for this PDF restricted to the support. And instead of writing this N and P as subscripts, we just bring them after the semicolon, and K is that same K, the query point. And if I want the CDF restricted to the support, at K, I have to add all the values from start up to K, and I just add up all these PDFs. The actual PDF and CDF not restricted to the support but valid for the full real line will require these filtering functions, and this is something you have been used to. So you have used this over and over. Just to give you a visualization of how this PDF will look like, if you choose, let's say, some typical values. If N is, for example, 5, and let's say P is 0.2, so I can say that, okay, the possible values are 0, 1, and so on up to 5. So at 0, I will have no success, so I will just have 1 minus P raised to 5, because all failures. And this will be one of my probabilities. The other extreme will be 5 successes, no failure, so that will be P raised to 5. Now we know that 1 minus P, which is 0.8, is greater than P, so which means that this probability will be larger than that probability. That will be smaller. And this probability will be larger than this because there are many ways of achieving one success. There was only one way of achieving no success, and there are at least 5 ways of achieving one success. So that's why you will have to increase the probability. Similarly, there is only one way of achieving 5 successes, but there are more ways of achieving 4 successes, so this probability will be larger than that. So actually, somewhere in the middle you will have that maximum probability. If we want to characterize this distribution by our favorite mean and variance, we can also do that. Instead of using the formulas, we just recognize the definition. What was the definition of binomial random variable? Because it is the number of successes in n trials, we saw that it was a sum of n Bernoulli random variables, all independent. Yeah, so we can use now the expectation rule and the linearity of it. I can simply apply the expectation operator at x, which is the sum. So if I apply this expectation operator to a sum linear operator, we know it's a linear operator, so it can go inside the sum and I will have a sum of expectations. Each one of them I know is P because they are all Bernoulli, and we know the Bernoulli expectation of the Bernoulli random variable is P. So I will just add this P n times and I will have n times P. That's my expectation. Of course, if you want, you can also use PGF for that. Because we know the PGF of our new random variable, I can simply differentiate this and set z to 1. We can also do that. Yeah, but this is a much simpler way because we know that x is a sum of random variables. Remember, we do not need, although we know these random variables are independent, but that independence is not required for calculating the mean because E is linear and this linearity doesn't care whether these xi's are independent or not. In the next quantity, so if we want the variance of this binomial distribution, the variance of x is the sum of Bernoulli random variables. If we want to use the fact or the formula that the variance of this sum is the sum of these variances, that will require these xi's to be independent. Fortunately, they are, so we simply add up the variance of a Bernoulli distribution n times. Yeah, so it will be n times p times 1 minus p. We know the variance of binomial distribution. That, I mean, this is just a confirmation. You have already worked this out. One more thing is you must recall the meaning of failure and success in the language of Bernoulli trial. This should have nothing to do with how we see failure and success in the real world. So in the language of Bernoulli, success is the event to which we have assigned 1, and failure is the event to which we... So it's up to you. If you encode something by 1, that has to be a success in the language of Bernoulli, even if that is not a success in the real world. So in that language, you know, this x, which was binomial, it was the number of successes or the count of successes. What if we are interested in the number of failures? We don't need to reinvent the wheel. We just go with our original x, which is the number of successes, binomially distributed, and n trials, p is the probability of success. So because n is the total number of trials, and if I have x successes, it's a random quantity, and let's say I have y failures, so let's say y represents this number. So I know x plus y must equal n because the number of failures and the number of successes and the number of failures must be must be n. It cannot be smaller than n, it cannot be larger than n. So y equals n minus x, and I can use this transformation to work out the distribution of y. So if I'm interested in the PDF, I will have to understand or analyze this event, y equals k, which means the event that I have k failures. Now k failures can be rewritten in terms of x, y is n minus x. Now that means that I can have n minus k successes. Yeah, x is the number of successes. So k failures translate to n minus k successes, and which means that for the PDF of y, which is the number of failures, yeah, at k, I can simply use the PDF of x, which is the number of successes. The only thing is that I need to replace this k with n minus k, because k failures translate to n minus k successes, and for successes I can use fx. So I'm done. I have the formula for fx, I just need to substitute. I can also attack the CDF that will require me to analyze this event. the number of failures not exceeding k. Now if I replace y with n minus k, because of this minus sign, this will go to this side, k will go to this side, and what happens is that x, instead of less than or equal to, now x will be greater than or equal to n minus k. So in words, number of failures not exceeding k is the same as number of successes um, at least n minus k. Yeah, this translates to at least. So I can now work this out. Yeah, that was a simple substitution. The support doesn't change, so the number of failures will still start from 0. 0 means no failure, n means all failures, and that is standard. I just use the PDF of binomial, replacing k with n minus k, and the rest doesn't change. And I think maybe I got one thing wrong, because I simply had to replace k with with n minus k. This should not change. This is still p. Yeah, this is still p. Let me think. Let me think if I have got it right. So I know that fx of k, we need to work this out, yeah, is n, is because it is binomial, so it has to be nk, and p to kth, and 1 minus p to n minus k. Let's set k to n minus k and see what do we get. So it will be n minus k, it will be n minus k, it will be p n minus k, and it will be 1 minus p, and this will be k. Yeah. So in fact, because we just use that, so this will simply be p. Yeah. And if you want to simplify this, maybe we get some pattern. This will be, if I bring this 1 minus p here to kth, and this p to n minus kth, and I also know that this can also be n minus, if I subtract this from that, I will get k. So this can also be seen as, yeah, now maybe this is what I wanted to write. This can be written as a binomially distributed, sorry, the PDF of a binomial distribution. And let me just write it here, the PDF of binomial distribution, and still number of trials. But if I take this as my probability of success, it would be 1 minus p. Yeah, so if I swap success with failure, then this will be k. Yeah, so if I want to write k here, then I can write 1 minus p. Yeah, so I think you're following. I hope you're following with me. And because of that less than or equal to, let me go back, this less than or equal to, because this equal didn't change, it is still an equal sign. So that was simple. We just replaced k with n minus k. But this less than or equal to was replaced by greater than or equal to. So I cannot say that the CDF of y will be equal to the CDF of x. This substitution alone is not enough. Yeah, because we know this less than or equal to change to greater than or equal to, so it will be a different quantity, because we now have greater than or equal to for x greater than or equal to n minus k. So it has to start from n minus k because it is equal to, and greater than mean that I have to look for higher values, n minus k plus 1, n minus k plus 2, up to the largest possible value, which is n. So that is how you work out the CDF of number of failures. Let's apply this distribution, the result of this distribution, to bit transmission. So it's an interesting problem. Let's say I have a channel and I'm sending bits. I'm sending bit, and the received bit could be corrupted, so which means that a 1 could be received as a 0 in case it gets corrupted, and a 0 could be received as 1. So the probability of this error, a 1 converting to a 0 and a 0 converting to a 1 after reception, let's say that probability of error is 0.0001. In the language of communication engineers, it is called the bit error rate. Don't call me why they call it rate, because rate is something with respect to time, but yeah, don't ask me. They just call it rate. So for us, it is the probability of an error. Yeah, either way, either a 1 received as a 0 or a 0 received as a 1. So now to deal with this error, because this for you it may be a small probability, but for communication system engineers it is not a small probability. So they would like to somehow deal with that. So instead of sending this bit only once, imagine there is a scheme where you send each bit 5 times. So you can think of it as n trials or 5 trials. So you send the bit 5 times. Yeah. You send it again, you send it again, you send it again, you send it again. So you send that 5 times. So 1, 2, up to 5. You can think of it as 5 trials. And here you look for the majority. Yeah. You hope that it will be highly unlikely that all of them are received an error. So at least if the majority of them say something, we should believe that. So for example, if 3 of them are ones and 2 of them are 0, you will declare that it is a 1. So now let's say we are interested in the probability that the receiver will still make an incorrect decision, which means that the majority of those 5 are received wrong. Yeah. So for that we can, so remember we are interested in the incorrect decision. So if that is my purpose of solving this question, this getting a bit wrong or bit error is actually my success, because I'm interested in that. I want to assign 1 to that so that I can count it. So if x is now the number of bits in error, the number of bits in error out of those 5, of course that will be binomially distributed, 5 trials, because you are sending it 5 times, and p is the probability of success. That was the error rate. Yeah. And error for us is the success. So how do we represent the event which is informally written as the incorrect decision? Incorrect decision would mean that the number of bits that were received wrong is still in the majority. And you know, in 5, if you have 5 trials, in 5 trials, the smallest majority is 3. Yeah, so 3 is a majority, 4 is a majority, and 5 is a majority. 2 and 1 are minority. So all I need to calculate the probability of incorrect decision is to know the probability of x taking values larger than 2, so which means 3, 4, and 5. So I just have to add up, because these are mutually exclusive, I just have to add up the PDF of binomial distribution from 3 up to 5. You see that they all are greater than 2, and they all represent the incorrect decision, because you will have more errors than non-errors. And if I add this up, make the calculations, I get a probability that is much, much smaller than the original probability, that was 10 to minus 4. So if I just send 1 bit, this is the probability of incorrect decision. But if I send 5 bits and then take the majority, I have reduced that bit error effectively to a much smaller probability. That's the, of course, it will need more time, because you will have to send it 5 times. but you have improved the accuracy of the system. Let's move on to the second question. So the first question in that list was, remember we were actually interested in 4 quantities. One of the quantities was the number of successes in a fixed number of trials. Let's say n is fixed. So we are done with that. That is binomial distribution. The second quantity of interest is to count the number of trials. So you keep trying and you count the trials until you get your first success. So number of trials until your first success. Now there you could add the indicators or Bernoulli random variables from 1 up to n, because this n was known. Yeah, and this n was known, so there was no randomness there. The randomness was only in the sum. Yeah, because the randomness comes from here. Some of them will be 1, some of them will be 0. You don't know. So this x will be a random quantity, which you call the binomially distributed random variable. Here it's a different scenario. Here you don't know how many trials will you need to get that first success. So we write that first here as a sum. Here the sum was uncertain and the number of trials was certain. We knew it has to be 9 because that was part of the experimental condition. Here it's the opposite. Here we fix the number of successes to 1 because we are looking for that first success. So we fix the number of successes to 1 and we leave the number of trials needed for that first success open, because this will be random. Sometimes you will be lucky, you will get it in the first trial, but sometimes you will have to wait for 10 trials and maybe you never see that success. So k is a random quantity. That is what we are looking for. So let's say we want to, now that will be, k will be the number of trials. Yeah, so I am just using k for this random variable, and to find out the distribution of that, I can consider this event, the event that the number of trials needed for the first success is k. In other words, I am now considering the event that my first success was observed on the kth trial. Yeah, so if I replace, now I do not have a simple formula for k, but I know the meaning of k. This k taking this value is the same as replacing that k with that value. Yeah, so now you want, now this is your event basically. I just repeat that. Yeah, k trials giving me that first success. Now because I want this to be my first success, that must happen at the kth trial. Yeah, because that is one where you stop. If this success was before k minus 1, then that was not the first success. Yeah, so then this would be a wrong question. So here the meaning is clear here. You want k to be the last trial in that sequence, because it has to stop. The moment you see that first success, you have to stop. So, which means that this success 1 has to be observed at the kth trial. So that's why I'm writing xk. So the kth trial gave me a success. Yeah, very nice. And now that I must have an AND, because that alone is not enough. All the previous trials from 1 up to k minus 1, because the kth one gave me a success, they all must have given me a failure. 2 reasons. First, I only need to have 1 success, and that success must be the last of those k trials. So which means that from 1 up to k minus 1, I must have failures. If any of these were 1, then this whole event was wrong, because then I should have written a smaller value of k. So remember, because these are independent trials, so these two events will be independent, which means that if I take the probability of this intersection there, it will be simply the product of these probabilities. Yeah? And this will be valid for all non-zero integers, yeah, starting from 1, 2, and so on. So this, if you think about it, because this is an event related to one trial, and you know each trial, the indicator of success in each trial is Bernoulli, so I just use the definition of Bernoulli. Here I have k minus 1 trials, so now the value of number of trials is this time fixed to k minus 1. So I'm now asking for the probability that 0 successes were observed in k minus 1 trials. That is binomial distribution. 0 successes in k minus 1 trials, each with probability p of success. Multiply, because these are independent. If I multiply, I get this. You can also understand it this way. 1 minus p, failure. You observed k minus 1 failures, and the last one was a success. I think you have seen this many times. And if you want to determine the PGF, that's also very easy. Just apply the formula of PGF, apply this PDF there. Yeah, each PDF, the PDF at each point is multiplied by z to that value. And if you simplify this, actually it is a geometric series, because if I take this p out, and if I take one of these z out, I'll be left with z to k minus 1. Yeah, so this k is k minus 1 plus 1. I just take z to 1 out, so z is to k minus 1, 1 minus p is to k minus 1. I combine them, it is 1 minus p times z k to k minus 1, and this is a ratio of my geometric series. So this is just the sum of a geometric series, infinite series. I will find this expression useful for calculation of mean and variance and so on. But let me now discuss something very important, which is unique to geometric distribution among all the discrete distributions. So let's say that I am waiting for that first success. These are trials. Let's say I'm indexing the trials, and this was trial 1, this was trial 2, and so on. And let's say I imagine a scenario where no success is observed in the first m trials. I can describe this situation by the event k greater than m. Now, why greater than m? Because k by definition is the number of trials to get that first success. Because I here suggest or imagine a scenario where I have not observed that success, which means, so k is not just the number of trials, it is the number of trials for the first success. So which means that I have to wait beyond m. Nothing happened so far, so that first success has to be somewhere there. It was not there. Remember, if I ask for k less than m, this would mean that my first success was within these m trials, but that is not what I am asking for. Yeah. So in a way, what I'm suggesting here is that success will be starting from here, excluding m, and the success can be anywhere in this range. This is my k larger than m. Now let's say I want to ask a question right at this point. I want to say, okay, I was unlucky, I could not observe a success. What is the probability that the next k successes are still not fruitful? So next k would mean that this will be m plus 1, m plus 2, and this will be m plus k. Remember, I am looking for the further k trials, k further trials. So I want to ask for the probability that this first success will still be in future. It will still not be observed even in the next k trials. So m and m plus k. So if I start the counting from here, nothing happened till the mth trial, and now nothing will happen in the next k trials. So k greater than m plus k is this event. Yeah. So I have indicated this event and I have indicated this event. Now I want to know whether this knowledge, yeah, the fact that I know this, because maybe I don't know anything. I just start counting at m and I have I just disregard the fact that there was no success there. So if I want to know the probability of this later question, yeah, given that I have the information about the first m trials, I want to know whether this event has any effect on that event. I can anticipate that there should be no influence because of independence. All the Bernoulli trials are independent, but I still have to verify this. Now remember, if you want the probability of one event conditioned on another, you take the intersection, and the intersection here is simple. This event, yeah, from this point onward, is a subset of that event. It is actually contained in that. So these two, if you take the union of these two, you will take this event. So which means that the probability, let me read this out. Given that no success was observed in M trials, the probability that I will still not, because this greater than means still not, I will still not observe the first success even in the next k trials, yeah, starting counting it after m. This probability will be the probability of the union of, the intersection of these two, and because this is a subset of that, so I just take the subset to be as the intersection. I apply the formula for geometric. I know k greater than m means that all the m's were failures, so you raise 1 minus p to m. Here k greater than m plus k means that all m plus k trials were failures, so now you raise 1 minus p to m plus k. The m and m will cancel out and you are left with 1 minus p raised to k. Now this is interesting because this result does not depend on m. We chose m to be some value and we can change that value and this answer will not change. So as a special case, I can set m to 0. So let's set m to 0. That will be 0 plus k, this will be k. And I know the answer must not change because it does not depend on m. But what is the meaning of setting m to 0? Setting m to 0 means that previously I considered the observation that nothing happened till the mth trial. Even if I know that m, setting that m to 0 means that I am asking that same question at point 0, which means that I have not even started the trials. So this knowledge did not help me. Yeah. So whether you consider this into your question or whether you exclude this, you will still get that answer. So this can now be seen in two ways. This probability, because numerically it's the same, let me give two meanings to this. When we looked at this from that angle, it gave me the probability of no success, because this is no success, in the next k trials. Next K trials means further K trials, having observed no success till M. And here, because we have set M to 0 there, now this same quantity, numerically is the same, this also can be viewed as probability of no success in K trials. K trials mean that I'm not talking about next, I'm just counting it from the start. So this process has no memory. That's the point. That's the crunch of all, the punchline. So let me read this out. The probability of no success in the next K trial does not depend on how many trials have passed without a success. That's the precise sense in which we say that the geometric distribution is memoryless. So, but the physical reason behind this memorylessness, or behind this lack of memory, is actually the fact that the underlying sequence of trials is independent and identical. That was the reason. Yeah. So don't go for this fancy math. This math was just to convince you. The physical reason was the independence of trials. It had to be memoryless. There was no reason. A question that should come into your mind is that if we repeat this for the binomial distribution, we will not see this. Yeah. Because in binomial distribution, the number of trials is fixed, and when the number of trials is fixed, as you go, you see, if you look at this distribution, we discussed this there, because the number of trials is fixed, so the peak of the distribution is somewhere in the middle. So knowing something about the number of failures or the number of successes actually does change your probabilities. So memorylessness is a unique property of geometric distribution. Now we can also work out the properties, and remember, this version of geometric distribution where we are counting the number of trials until the first success is represented by, so if we write x there, sorry, if we write, I think we used k for that, that k is distributed according to geometric distribution. P here is the probability of success, and we write 1 there because the number of trials, the smallest value is 1. You need at least 1 trial to get that first success. So note this one corresponds to where the support starts. If you want to use PGF, we have the expression for PGF, differentiated, double differentiated, set Z to 1, and you can work out the mean and variance. Yeah. I will not derive this because you can do this at home. I will only try to interpret this result. The expected number of trials needed for the first success is 1 over P. Now this makes perfect sense. If P is small, which means the success is unlikely, 1 minus P will be large, which means that you would expect more trials to see that first success. If P is large, which means that if it is nearly equal to 1, this 1 minus P will also be, 1 minus P will be small. So the expected number of trials will also be small. And the variance of this K, if you work out all that formula, it will be 1 minus P divided by P squared. Yeah. So you can try to give meaning to this as well. Alternative to asking the question of number of trials, so when you ask the number of trials, first trial, second trial, and let's say you saw your first success on trial number K, this, let's say, imagine this is your first success. You count this also in your number of trials because you are counting trials, you're not counting failures. But you can also ask another question. You say, okay, I'm not interested in that last trial which gave me success. I'm just counting the failures before that. So let's call that J. So J will be the number of failures before the first success. Yeah, you still have to see that success, but the counting stops. So if j is the number of failures, and we will write this as geometric with subscript p and 0 as the superscript, because you can have 0 failures before first success. It is possible to have so if your first trial is a success, you will not count it, you will just count the failures before, and you will have 0 failures. So this will start from 0. That's why the notation has that 0. So if you want to find out the distribution of j, you can consider this event. Yeah, you want the sum of those Bernoulli random variables to be 1, because you still want that first success. Because you see, counting the number of failure doesn't mean that you are not looking for the success. You still want that first success, but j now just includes the failures, and you have to add that last trial which gave you success to give you this equation. And the probability of this equation can be actually the event that number of failures before the success is k is the same as, remember this k was the number of trials, is the same as you needed k plus 1 trials, because you just add that last trial. The advantage of phrasing it this way is that you can use the previous distribution. Yeah. So that p comes here after the semicolon, and you replace k with k plus 1 if you want to use the formula of geometric distribution. And that's, even if you forget about this math, this formula makes sense, because p is the last trial, the success on the last trial. P is the probability of success on the last trial, and this k now, because this k now is a value of j, not a value of upper k. This k is the number of failures. So you observed k failures, yeah, 1 minus p raised to k, before the first success. And if you want to find out the PGF, properties of PGF will allow you to see that, okay, that shift could be realized by simply multiplying the PGF of that unshifted geometric random variable. You just multiply it with z2 minus 1. This z2 minus 1 actually represents this k minus 1, the minus 1 thing. So what are the properties of this new shifted geometric random variable? Because you know j is k minus 1, it's a simple transformation, linear transformation, so the expectation will simply be the expectation of k minus 1. We know 1 minus p is the mean of that k. You subtract 1 from it, linearity, you get the mean of this shifted random variable. And that simple shifting does not change variance. Yeah, because when you write j as k minus 1, this k is independent of 1, because 1 is Dirac, and any random variable is independent of Dirac, because it's a deterministic quantity and this is a random quantity. Deterministic quantity will be independent of any random quantity. So I can apply the sum rule for variance. Yeah, and the variance of 1 is 0, so the variance actually doesn't change. That was all. In the next lecture, we will start with the next question, and that question will be to count the number of trials until the rth success. So instead of waiting for the first success, I'll be waiting for a fixed number of successes, and that will give me a new distribution. So, okay, see you next week.